Hello again. My name is Greg Westwater, and once again we have Bill Oberkampf joining us. We're both members of the NAFEMS Simulation Governance and Management Working Group. And when we last chatted, Bill, we had just finished talking a little bit about, the validation domain of simulations and cases where we're handling something that's very near to that validation domain. And that obviously kind of begs the question of, how do you define near? How do you know if it's close enough to that validation versus being, something that's way out there? So are there any tools, any, guidance? Is that just engineering judgment? Get a group of experts and pick their minds? How do we make those kinds of determinations?
Okay. I think I mentioned last time, Greg, that's the hardest question you've ever asked me. And we need to get across why that is such a difficult question. You ask, what does near mean, and then tools. Okay, let's talk about why near is a difficult question. Because near has to do with two kinds of things. One of them is, what are the physics that are occurring near where you have validation data? And then how does the physics change as you move away from near, okay, and you get far away? That's one question, okay? And you say, what do you mean like far away? For example, if you do an experiment in a laboratory at a given temperature and your facility only can do it over a very short range or a small range of temperatures compared to what the real equipment will operate, maybe it's a full up system, then there are extrapolations, we call it, maybe for very cold temperatures or very high temperatures that you can't do the experiment. You don't have the equipment. So you see, that's a physics effect, okay? Mm-hmm. And then the other one has not anything to do directly with how physics changes. It has to do with our models and how they change. As we talked about the last time in the validation domain, we assess model accuracy. That is the model, the physics modeling accuracy. But that accuracy changes over what we call the input space. And the input space is all of the parameters that describe the system and the environment. Their geometry parameters, their flow rates, their temperatures, their pressures, their loading, excitation, all kinds of things. And so when you put all of these together, our model accuracy changes over this space, okay? For example, if you say we're going to assume beam elements or shell elements or whatever you're going to do, the accuracy of those approximations change as we change the structure, the thickness, and the materials and all those kinds of things, okay? So those are the two kinds of things that affect the accuracy. So when you ask, are there any tools available? I'm not aware of any tools in this. And I think I know that's an active area of research. So people need to think of, what does near and far mean in terms of how does the physics change away from where I have data? And how do my approximations usually they get worse the further you get away. So think about it in that respect.
So I'm thinking, as you were answering there, if we get a big enough or diverse enough group of experts together, we might be able to anticipate, these physics are going to change, and realize that we're moving in, out of that near and into that kind of that far extrapolation. But the accuracy of the modeling, the numerical side that you're describing there, sounds like that's a lot harder to predict, or that's much more of an unknown as you go there, kind of a thing.
It really is. Let me give you one other example, because on these complicated questions, I think examples are very instructive. People will say, what are you talking about? Let's take the crash simulation of crash dynamics of an automobile. When you do a crash up simulation and also a test, there's a tremendous amount of calibration of parameters in the model. You do the experiment and you calibrate many different parameters. And then you say, let's suppose it's a head-on crash at, however many miles an hour, kilometers per, hour. But now you say, what is the accuracy of my model if we do a crash at an angle or a side impact crash? you see your parameters were not calibrated for those conditions. And then because the crash is extremely complicated, because you have large deformation, you have things tearing, you have bolts breaking, you have ripping of welds, you have all kinds of things. And these are very highly calibrated models. So that is a good example of, oh, that's a long way away from the front-on collision test. So that's another good example.
Okay. Yeah, I'm kind of reminded a little bit of I think, the old maps hundreds of years ago. They mapped the known territory, and then they just kind of, here there be dragons. Not everybody came back that went out there. So
That's
so
right.
I think it's a little bit the same kind of user beware as we move into those domains there that we haven't been able to validate in.
Yeah, I think they're at least as bad as dragons, if not worse.
So you talked about, there's times we can't do the testing just because of practical limitations, or and some of that's budget driven. For a small inexpensive widget, we're not going to invest significant test capacity. But on the other extreme, we do have things like I'll say a nuclear power plant. We're not going to melt down a nuclear reactor in order to get a validation data point. There's some very valid reasons why we can't always validate some of the conditions that we want to simulate to cover those upset conditions or those worst case scenarios.
Mm-hmm.
So how do we handle it when our simulation, when we have to go into that, kind of that far out extrapolation beyond our validation domain? What are the techniques? How do we quantify that uncertainty?
That's a very important practical question. And the usual procedure is to think about, how do we use what we call the validation hierarchy, or you could call it a system hierarchy. So maybe we can't do the full up test of the full piece of equipment, let's say at the proper temperature or pressure or loading or whatever it is, like a nuclear power plant. But we can do subsystems, or we could do assemblies or sub-assemblies or components for these high temperatures, high loadings, high temperature, high pressure. And for safety issues, we can say, and these are of like subsystems or assemblies, sub-assemblies. So we start assessing, how well does our model predict the experimental results at maybe pretty close to full conditions, but it's just of one subsystem or one assembly. That's how we start to build confidence in it. And it's not a test of our model for the complete system, which you say, because of budget concerns, schedule concerns, or environmental concerns, we can't do the full up experiment. But how could we do them, particularly on safety critical systems, for elements below the top of the hierarchy? So that's one approach.
Okay. And so from those individual subsystems, does that help us then kind of quantify the total uncertainty of our whole system? How do we get to the point where we're starting to estimate, that error or uncertainty for those extreme conditions?
Okay. I'll pose the question this way. If you have a full up system and then you have subsystems, maybe you have a compressor, you have a turbine, maybe you have some sort of igniter system, or you have all kinds of other systems. And then if you can do experiments over a broader operating range for those conditions, and then you have uncertainty in each of those models. And then when you put them all together for the complete system, we can try to get an estimate of the uncertainty of all of the contributors that we've talked about before. There's not only model form uncertainty, but there's numerical error uncertainty, and there's also other kinds of uncertainties in the conditions. And when they go up into the hierarchy, then we have the coupling of these systems. And if nature was linear, we could do the problem and estimation of uncertainty of the complete system very well. But nature's much worse than that. It's nonlinear. And so when you put all of these systems together that operate in a nonlinear coupled way, that's why that estimation of total uncertainty A lot of research is going on in that. It's usually called roll-up of uncertainties as you go up the hierarchy, but nobody really knows how to do that right now.
So there's a lot of kind of user beware or be cautious as we move into those domains there.
That's right.
I think in one of our side conversations at one point, you talked about, sources of uncertainty about, the input data, the numerical solution error, discretization errors, things like that. And the idea that we tend to assume that those errors remain fairly constant as we move out into these extrapolated applications, but it's that model form uncertainty that becomes the really unpredictable element. So at least we have kind of some sort of a baseline, but still, I think that just comes back to that. Just we've got to be cautious that we're not extending our models too far.
Yeah, and one relatively new idea that it's mainly research in research journals, where if you say we cannot afford or we're not allowed to do an experiment on the complete system, or it could be a subsystem, very far from where we are right now in the validation domain. One idea is that you use higher fidelity physics models for these other conditions, for these conditions you can't test. And the argument is that if I use a higher fidelity physics model for these other cases, and we think of that as experimental data, of course it's not, it's still a simulation, but that might help us inform what is the uncertainty with our simpler model. And some people even use it to calibrate the simpler model for these other conditions. So sometimes it's called multi-model or different fidelity models. That can help if we can't do experiments at these other conditions. So that's one approach, but it is still a modeling technique. It's not experiments.
That's very interesting. At the very least, it would help us know that we're not sensitive to some of our modeling decisions.
That's right.
But so I think one of the things you're telling me, Bill, there is, we don't have good hard and fast tools. And so really, I think this becomes something that's really important to be a collaborative decision that, a single analyst, whether you're a novice or somebody who's got 20 or 30 years of simulation experience, probably really wants to be collaborating with fellow experts to really understand the potential risk and pitfalls when we're moving into these conditions that are far away. It sounds like to me that's just absolutely critical to help know, hey, am I doing a bad thing here?
Yeah, no, it's a good practical suggestion to have different analysts maybe redo the simulation or look at the approximations and assumptions, because as you change those, you change the model form uncertainty or the model form error. It changes. So maybe different analysts, they typically will pick different models. And the other thing that's a practical issue on that is to communicate to the decision maker. Could be the project manager, could be middle management, whatever, the safety group. Let them know that these are uncertainties, and you can try to estimate them. They're not easy to estimate. You can get a reasonably good estimate of something like discretization error at these large extrapolation conditions. That's a numerical error. But the model form uncertainty, that is really difficult because you have no data there. So maybe you can use these different fidelity models. But I think the responsibility is on the computational analyst to communicate those uncertainties to the decision makers, because one thing a decision maker doesn't like is they don't want to be surprised. You can tell them, I'm really uncertain on that, and a good manager will say, okay, I'll feed that into my decision making, and maybe he'll come up with the money or the schedule to do this experiment if he's worried, because a decision maker, a manager, is a risk manager, a project. That's what he does. So
yeah.
that's a practical way to look at it.
Yeah, and I think there's terms kind of some safety numbers too. If you get the less fortunate circumstance where they just want an answer and go, and want to take it further than maybe you were comfortable with, I think that's where you got the value of, hey, the 3 or 4 of us or whatever have collaborated together and we all have this concern. That
Yep.
helps make it easier to have some of those conversations and feeling like the lone prophet in the wilderness. So,
Yep. Absolutely.
well, thank you very much for your time today, Bill. I appreciate it. And we look forward to next time we get together.
Pleasure, Greg. Thank you.